Hello, my name is Vrålstad, and today I will talk about REFoCUS with spatial weighting. This work is a joint collaboration together with my co-authors. REFoCUS is a method for recovering the multistatic dataset from any arbitrary scan sequence. It is published by Nick Botnes, and the concept is illustrated by this figure. Here, every focus transmit in the scan sequence are back-propagated by the applied transmit delay for one selected element. By coherently compounding the back-propagated received channel data, the received signal for one single element transmission is recovered. We found REFoCUS interesting, but faced a problem when we tried it on micro-beamformed data. Micro-beamforming is processing done on the probe itself to reduce the number of channels. This creates grading lobes, which are important to mask out, something REFoCUS did not do out of the box. We tried the conventional and the Fourier methods of REFoCUS with regularization, without luck with this dataset. We did, however, solve this using a time domain implementation and by weighting pixels with clutter down. The agenda for this presentation is as follows. I will first explain the key concepts and differentiation from the original REFoCUS method with our method. Secondly, I will explain some weighting functions, followed by a time domain implementation. Then I will show how the spatial weighting is beneficial for beamforming in low SNR settings, before I show the example using micro-beamformed data. The conventional REFoCUS method obtains the multistatic dataset using a recovery process. The recovery takes into account the aperture weighting used on transmit. This multistatic dataset is beamformed to create the image, and the multistatic beamformer weights pixels according to the directivity and desired F-number of transmit and receiver elements. We introduce the spatially weighted REFoCUS, which performs the recovery and beamforming stage in one go and weights the pixels to accommodate physical principles and image quality. The array aperture weighting can, for example, look like this. Here we show the first wave transmission, with white elements being the active and black elements being inactive. This is a stepped scan sequence, and we can see that for the second transmission, the active aperture has shifted, and this continues until we reach the last transmission K. Another type of weighting is the element directivity or constant F-number weighting. The weighting models the angular sensitivity of transmit and receiver elements. The geometric wave weighting models the intensity of the geometric beam for a focused transmission. Yet another type of weighting is grading lobe masking. Grading lobes occur as predictable steering angles and is dependent on the pitch of the array. The mask is set to only include signals inside a grading lobe-free span of angles. Masking is applied when coherently compounding during recovery and beamforming. We now want to illustrate the spatially weighted REFoCUS method by investigating the time of flight calculation. One focus transmit event with focus position V and transmit origin O on a curvilinear array is visualized. This pixel position is noted at R and element position E. The transmit wave at time 0 looks like this and will propagate towards V. The transmit wave time of flight to pixel R is visualized like this and the received time of flight like this. The two-way time of flight is interpolated on the received channel data and give one sample for the one transmit, receiver, and pixel. For REFoCUS, on the other hand, we have multiple transmit time of flight, like this. This corresponds to the active sender element for this transmit and give multiple time samples in the channel data. The pixel-based beamformer with REFoCUS and spatial weighting is captured in this equation, which is a coherent compounding of n sender elements, k transmit events, and m receiver elements. We note here that the weighting function W is a function of pixel position, receiver element, transmit event, and sender element. The time domain pixel-based beamformer is implemented using the weighting function mentioned. My colleague Magnus will present a poster on VBeam, titled here. VBeam is the new open-source Python library running on the GPU, designed to merge beamforming with machine learning. It is now available on GitHub. We now consider a phantom acquisition where we have transmitted with low pulse voltage of 6.3 volts on the Vrålstad system using a 1D Philips L7 probe. We used a stepping aperture scan with focus transmit and image desist indicated. Before we show the results, let us investigate why spatial weighting is important for signal-to-noise ratio. Here is a focus transmit simulation in K-wave with 2-point scatters around the transmit focus. The transmitted energy will be higher inside the geometric beam, and signal received from this region will have higher signal-to-noise ratio compared to outside where the edge waves are dominant. The amplitude of the reflected wave from the point scatters are shown to be lower outside the beam. Recovering and beamforming signals from outside the beam will result in lower SNR. Hence, it is better to only keep signals from inside the beam, even though this neglects signals from the edge waves. The image we now see is the conventional REFoCUS method, which do not discriminate the low SNR regions in the recovery. This produces a noisy image with low contrast in the no coexist. Some of the noise can be suppressed by using a narrower directivity weighting at the expense of resolution. The spatially weighted REFoCUS method weights down the low SNR regions with a geometric wave weighting, suppressing the noise and obtain higher contrast. The contrast is measured with GCNR and use regions indicated inside and outside this. We now turn to a second experiment using a sub-aperture microbeamforming probe. The microbeamforming is done to reduce the number of channels, and the reduction in channels will produce grating lobes. We use a 2D curvilinear matrix array probe called EM6E from the GE Healthcare Vrålstad. We use stepping scan with focus transmit and create 2 images with REFoCUS. The first image performs conventional REFoCUS. The second image performs REFoCUS with spatial weighting and suppress the grating lobes from the sub-aperture probe. The 2 images are shown here. They both use similar F-number directivity weighting, but the second image also performs grating lobe suppression by masking angles around the transmit beam. The GCNR contrast measurement using hand-drawn regions show an increase in the spatial weighted image because the grating lobe has been removed. The GCNR goes from 0.56 to 0.81. We have chosen an in vivo case to show this behavior because of the high dynamic content. Here is the close-up image shown. In summary, we have demonstrated that spatial weighting is beneficial and in some cases necessary to obtain desired image quality when using REFoCUS. We claim that the generalization shown here enables time domain beamforming of all scan sequences with REFoCUS. Thank you for your attention.